Well, welcome back. We're going to get right into our first speaker. It's beautiful out here in Breckenridge. It is in the teens right now, but we're inside to learn about science, and we're here to learn about technology and climate science as well. Our first speaker of the Weather and Climate Summit is Dr. Bill Lapenta. He is the director of NOAA, National Weather Service's National Centers for Environmental Prediction. To get you a little bit familiar with Bill, we have a short video that you can take a look at, and then we'll come up live with Bill's presentation. So take a look.
Hi, my name is Bill Lapenta, and I'm the director of the National Centers for Environmental Prediction, which is part of the National Weather Service. There are 9 centers at NCEP, some of which you might be familiar with. The Storm Prediction Center in Norman, Oklahoma, the National Hurricane Center in Miami, Florida. I want to thank Dave and the sponsors for inviting me to the Weather and Climate Summit. This is the first time I've participated in this event, although numerous people from the National Centers for Environmental Prediction have participated. So again, this is a great opportunity. And I just want to say that I thank everybody that's here participating, because I know you could be doing some other things. And I thank all those folks that are online watching us in real time, because again, you could be doing other things. People are extremely passionate about the weather. I'm passionate about the weather, and I've been passionate since I was about 8 years old. And I think many of us in meteorology are that way as well. So what I want to do today is I was asked to talk about operational numerical modeling. So that's what I'm going to focus on today. And you're going to have other folks from the National Centers here, Rick Knabb from the Hurricane Center, Paul Cosin from the Weather Prediction Center, talking more about the products and the way that they make forecasts. So what I'm going to focus on are some foundational tools that are used to support the weather enterprise. So my outline today, and I want to keep this relatively informal, I'm just going to talk about the Weather Ready Nation, some changes that are occurring in the National Weather Service here in the US, and then touch on the National Centers for Environmental Prediction, what it is we do. Then I'm going to talk about the numerical guidance, or the production suite, as we call it, the models that we run every day and that people rely on. And I'll talk about the supercomputer as well. Then I'm just going to talk about some of the basics of numerical weather prediction that we could perhaps talk about in a conversation. The model development process. This is a really important part in an operational organization that perhaps is not fully recognized in research. I'll touch on ensemble systems, because the day of a single deterministic run that's past us now, looking forward to probabilistic information. Then I want to talk about the Hurricane Sandy event of 2012 and how that really had a profound impact in the modeling in the US. And then some thoughts going forward on how the production suite is going to evolve in the next 10 years. So again, I want to keep this relatively informal. I want to provide you with some insight to what I've learned in the last 6 years being at NOAA in an operational organization. My first 20 years in the field were spent at NASA, Marshall Space Flight Center in Huntsville, where I was doing research on mesoscale modeling, working closely with the Weather Forecast Office in Huntsville. And in doing that, I thought I kind of knew a lot about operational meteorology. And once I stepped into the doors at NOAA, sat in that seat for a while, I quickly came to realize that I had a lot of misinformation. A lot of things that I thought about operational modeling, per se, really were not accurate. So I want to share some of those insights with you today. So the Weather Ready Nation, excuse me. Last year you had Chris Strager was here talking about the Weather Ready Nation. Dr. Uccellini came on board as the director of the Weather Service about 2 years ago now. And he has assembled a very aggressive campaign to make substantial changes within the Weather Service. And out of that comes what we call the Weather Ready Nation. And it's community resilience. It's really ready, responsive, and resilient to high impact events. And in the last year, Dr. Uccellini has gotten significant changes made to the National Weather Service, such that we now have a new headquarters reorganization that's been approved by Congress. We also have a revised budget structure as well, approved by Congress. And so we are now starting to operate in a new structure. And the main point about the Weather Ready Nation is that we're really focusing on the communication. Yes, we've had a lot of great technological advances in meteorology and atmospheric sciences through observing systems, modeling systems as well, and just our increased knowledge of atmospheric processes that help predict better. But it's getting that information to the end user in a way that they can make informed decisions. And that's really what Weather Ready Nation is really about, is going that last mile. What good is the information if you can't communicate it in an effective way to your end users? And people in this room are considered customers and end users of the products and services that we provide in the National Weather Service. So there's been a lot of emphasis on this. Last week at the American Meteorological Society meeting, a lot of talk about Weather Ready Nation, and I'm sure you're going to hear more about it as time goes on. So this is just an example about a high-impact event that occurred in November, lake effect snow in Buffalo. I'm sure you're all familiar with it. We are aggressively looking at these events in the National Weather Service and trying to coordinate and communicate well ahead of time what the potential impacts might be. And in the end, it's all up to what the end users do with that information. So what we've seen is a trend in the sense as we get better at communicating to the public, to our stakeholders, emergency managers, and the media like yourselves, we see them taking action. And what's happening is when there is a misunderstanding or perhaps misinformation and people make accusations, we're finding that people are coming to the defense of the National Weather Service like never before. We're not perfect, we're far from perfect, but we're making a concerted effort to get better and communicate our messages in an effective way and in a consistent way. That's one of the big emphasis that Dr. Uccellini has, is portraying and conveying a consistent message across the National Weather Service, across the weather forecast offices, across the 9 national centers, across the river forecast centers, and it's really important that we do that so we don't confuse our stakeholders. And I must say that this reorganization at headquarters and the budget reorganization is really forcing conversations, not just in the National Weather Service, but within NOAA, that I haven't seen in the last 5 years. We're asking a lot of hard questions, we're coordinating, we're being a lot more strategic than we've been in the past, and that's setting ourselves up to be accountable for information. So, moving on to the National Centers for Environmental Prediction. I've been the director now for the past year. Prior to that, I was a deputy director of the Environmental Modeling Center at NCEP, and then the acting director for several years there as well. And we have 9 national centers. I'm not going to go through them all today, but what I'm going to really focus on is the Environmental Modeling Center. That's the organization that has the primary responsibility for developing and transitioning into operations the numerical guidance systems that you use on a daily basis. Our vision at NCEP, we're in the process of going through a new strategic plan development. We've had a lot of stakeholder input, a lot of employee input. We want to be the trusted source for environmental predictions from the sun to the sea when it matters most. We want people to rely on our products and services. And back in 2000, when we had a supercomputer fire, our products and services were not very reliable. We've done a lot of work to make them on time every time, and people have come to rely on that accountability of our products and services. And that's something that we're very proud of at NCEP, and it's something that people rely on. So what we deliver, again, we have a very broad portfolio. We have the Space Weather Prediction Center in Boulder, Colorado, that issues solar flare warnings. We have the Climate Prediction Center in College Park that does seasonal outlooks. We have the Weather Prediction Center in College Park, which does winter weather forecasts, quantitative precipitation forecasts out to day 7. We have centers like the Storm Prediction Center and the Hurricane Center that focus on high-impact events such as hurricanes and severe weather associated with convection and fire weather. And we have the Aviation Weather Center in Kansas City that is really plugged into what the FAA needs and supporting them on a daily basis. And we also have the Ocean Prediction Center in College Park that does a global marine forecast. And that's something that we really don't talk about very much, but is absolutely critical to our transportation industry. And then underneath it all, we have NCEP Central Operations, which is really redefining the IT network within the National Weather Service, just not a support service to NCEP, but they are revolutionizing the IT network for the National Weather Service, which is really critical so we can get information to the weather forecast offices in a way we weren't able to do in the past. And also, they are responsible for maintaining, managing the supercomputer that we use for operations as well. So it's really a team effort at the national centers. And looking forward for the next 5 years, again, NCEP is going to be a major player in the weather-ready nation, helping to build it and sustain it. Strategic areas, high-impact events are becoming a big emphasis. And it's not just high-impact events, but extending the lead times associated with predicting high-impact events. And of course, you have to have the predictability and the technology underneath that and the science. We're finding that we're moving to a more of an integrated Earth system science approach. The days of having a single atmospheric model running by itself with no land surface connection or ocean connection, that's a thing of the past. As we go to longer lead times, we have to have a more holistic approach to what we do in terms of our science and our modeling. There's a lot of emphasis on providing products and services in the week 3 to 4. The president, a couple months ago at the National Climate Summit, mentioned that new initiative. And then again, strategically transitioning research into operations. That's a critical thing. There's a lot of work done by the academic community, by private industry, that could have a positive impact on the products and services that we provide. And NOAA has invested in what we call test beds, which bring together the academic community, private industry, with the operational forecasters and the development teams in the operational centers to help transition and communicate between those two organizations so that we can effectively transition a lot of research into an operational framework. Again, we're going to work with our partners in developing an integrated field structure across the Weather Service, and this goes to the consistency issue. Delivering consistent messaging, consistent products and services. Again, we're committed to providing world-class numerical guidance that supports the weather enterprise. Again, we're not going to deviate from timely, reliable, and accurate products and services. And underneath it all is infrastructure in terms of IT technology, supercomputing, that is absolutely critical for us to achieve our mission. Now, I'm going to move on to the modeling part of the conversation. The weather-ready nation, strategic goals, there are 6 of them. Weather, water, and climate. These should not be foreign to you. I'm sure you heard them last year. These are the primary areas for the Weather Service. We are looking at improving economic productivity through our products and services, healthy community and ecosystems, and you have to have a healthy workforce in order to achieve anything. So these are the 6 primary goals for the National Weather Service going forward. And underneath all that is operational numerical guidance. And I like to look at it quite simplistically as it's a foundational tool. It's one of the building blocks in the foundation of creating a weather-ready nation, and for that matter, really creating a national and global weather enterprise. Just like observations, just like supercomputers, these are foundational tools that are used by people in this room, people around the world on a daily basis that help them provide information to their customer base, and really it does drive the U.S. economic growth. Very important tools. That's why people, I think, are so passionate about modeling. So, the basic components of the modeling enterprise, it all starts with observations. Everybody knows that. A lot of what we do are initial value problems, and so you have to have good information coming into a system in order to at least have a chance of making a good forecast. The majority of the observing system, the volume, is dominated by satellites. There's been a lot of attention on that, but that's not to ignore what's happening on ground-based systems, aircraft information, a lot of information that comes from those types of observations. And then the data assimilation systems and the models. This is where you take the observations, combine them into an analysis, and try to predict what's going to happen to the atmosphere or your parameter of choice in the future. And you have to have sophisticated data assimilation systems which combine the observations with a model to get an initial state. And then you have to have the models themselves, which are the engines that predict the state forward in time. I'm going to talk about those a little bit later on in terms of, what are the building blocks of those models and why are they so important, and why do they differ depending upon the application. And another area that's rapidly growing is statistical post-processing and reforecasts. what we're finding is that, again, you're moving away from a single deterministic run, which is what we used to have when I was a grad student back in the 80s, to a more ensemble-based approach. And people and end users, quite honestly, are taking our model runs and creating calibrated products and services from those model runs, and also generating what we call reforecast to help them calibrate the ensembles. So it helps remove biases from the modeling systems, and it provides some very useful information. And one of the things that we're dealing with at NCEP is that the need for reforecast, even for the global ensemble forecast system, which is a medium range tool, is an emerging requirement. That did not exist a couple of years ago. But now it's existing. The community demands that we pay attention to it. So we're going to have to change the way we do business in our development of the global ensemble forecast system to include reforecasts. We respond to customer input. And then the last piece, high performance computing. I'm going to talk a little bit about that. There was a big announcement last week, excuse me, by Dr. Sullivan at the AMS, and I'll touch on that. So these are the building blocks of the numerical weather prediction modeling enterprise. I just wanted to show this. This is the first operational production suite in 1955. At that time, we were the US Weather Bureau. I wasn't born yet. But we basically had three components to the production suite. We had a baroclitic model, which was a 300-kilometer resolution system of 3 layers, covered the continental US out to 36 hours. We had a thermotropic model, 375-kilometer, 2-layer. And we had a barotropic model, 600-kilometer, 1-layer. This is what it looked like in 1955, and they were still able to produce weather forecasts, right? This is what the production suite looks like today. Each line represents a different component of the production suite. And I'm not going to go into great detail here other to say that what we run today operationally ranges from all the way on-demand smoke dispersion models, on-demand fire, high-resolution fire weather nests, on-demand regional hurricane models, all the way up to the climate forecast system, which produces seasonal forecasts out to 9 months, and then everything in between. The blue lines represent ensemble-based systems. NCEP was one of the first operational centers to aggressively pursue the use of ensembles. That was a move that I think has really paid off in the long run, and something that I'll talk about in a little bit further. But we have everything in between, a very broad portfolio of the production suite. And when you look at how the connections are between the components, each box basically represents a different part of the production suite. You could find your favorite system. The global forecast system is the green box. The global ensemble forecast system is right below it. On the lower right-hand part of the diagram is the high-resolution rapid refresh, which was just implemented in September of this past year. And then up in the upper right-hand corner, we have blue boxes. And those are boxes that are associated with marine numerical guidance systems, dealing with waves, dealing with storm surge, both tropical and extratropical. We have regional bay models that are operated and developed by the National Ocean Service. And we have ecosystem models as well, and everything in between. The reason I show this diagram is to give you a sense of the connectivity between all the pieces in the production suite. And the global forecast system really is the foundation. And if you look at this carefully, you'll see that it touches just about every other model in the production suite. So the better that system is in terms of its skill, the better the downstream systems are going to be. And so we've been paying quite a bit of attention to the development of the global forecast system over the last several years. We, in 2012, implemented an advanced data assimilation system, the 3D hybrid EN variational system, which gave us a nice increase in skill. And we continue to develop that. And I'm going to talk about an upgrade that is planned to go in on Wednesday, less than 2 days from now. And I'll talk about some of the results from that testing. But again, a very complicated and comprehensive production suite that we run here in the United States. This is what the production suite looks like on the supercomputer. This is a 24-hour cycle. The vertical axis represents the amount of computational capacity that's put to each one of the pieces. And each one of the pieces of the production suite is represented by a different color. So it looks very systematic, in other words, very cyclic. That's because we run a lot of our systems on a 6-hour cycle, or in other words, we run it every 6 hours. And you could find some of your favorite components. The high resolution rapid refresh, for example, is that yellow frequent stripe that's on the bottom of the diagram. Beneath that, in blue, is a climate forecast system. That runs 24/7. The light blue is the global forecast system, including the data assimilation system. The pink is the global ensemble forecast system. And those are the major pieces of our global components. And then you see the spikier pieces, the tall ones. They take a lot of computational resources. The HWRF, short-range ensemble forecast system, which is a workhorse for medium-range prediction, or short-range prediction, I should say, out to 3 days. That's in red. The North American model is in light green. And then we have the high-res window in yellow. The point here is that these run on a systematic basis. They run 24/7, and they generate a tremendous amount of information that we then provide to our customer base. It's a very complicated system, and the name of our operational computer is the NOAA Weather and Climate Operational Supercomputer System. It's not NCEP's operational computer. We manage it, but it's NOAA's asset, and it really is the asset of this community right here. I want to make that's an important point. So a lot of people ask me, well, how do you make decisions about upgrades? How do you make decisions where to put your resources? And what this diagram shows is the component, the percentage that each component takes in terms of the total production suite. And not to anybody's surprise, the regional systems are very expensive. That's because we have a large geographic area that we have to cover for the National Weather Service. The HWRF, for example, the minute it went in, it became the most expensive system we run today. And in operations, you have to look at the trade space. Everything costs, right? We're not a fundamental research organization, so we have to make trade-offs in terms of model complexity and how fast those models run on the supercomputer to provide you with useful information over time. High resolution rapid refresh, 22%. The North American model, 12%. Short range ensemble forecast system, 11%. Those are the three most expensive pieces. And then for the global system, the global forecast system there is at 5%. That's the deterministic model itself. And then the data assimilation is 2%. So a lot of people ask me about, well, how do you prioritize that? Some people think we spend too much on the regional systems. They'd like to see the global systems be increased. Well, I can tell you that with the next upgrade of the GFS that's going to come in 2 days, the amount of resources put towards the global systems will just about double. And that's because we're increasing resolution and we're increasing the complexity of the data assimilation system. So there's the regional systems. Again, consume about 45% of the total. This is something that I want to share because it really does separate us from just about every other operational and modeling center in the world, is the amount of coverage that we have to do. It's incumbent upon us to provide this high-resolution information to the stakeholders over the North American continent. And we have the North American model. We have the rapid refresh system that supports aviation, the high-res windows, which is really designed for convective severe storms. And then we have the short-range ensemble forecast system, again, which is a 0 to 3 day probabilistic system. These are very expensive systems to run computationally, and no other operational center in the world has this kind of geographic coverage to cover with regional systems. And that's just a fact. That's just something that we provide. The National Weather Service is geographically diverse and spread out. We have regions in Alaska. We have the Pacific region that we have to provide coverage for. And of course, we have to provide coverage for the Dominican Republic. So That's one reason why we're so spread out. Another reason why we have to run a number of different systems at high resolution, both in terms of spatial resolution and also number of runs per day. So I just wanted to share this with you, kind of just gives you a little bit of a perspective as to what it is we do here in the U.S. that no other operational center has to do. And it consumes a lot of resources. Now I just want to talk a little bit about the modeling process itself. Observations. We spend a lot of resources on observations. They're absolutely critical to the mission of predicting the future state of the atmosphere or any other field. And they're also critical in situational awareness and use by the forecasters on a daily basis. When we talk about observing systems, there's a lot of emphasis on numerical weather prediction, but it's just not numerical weather prediction. Forecasters rely on those data on a real-time basis all the time, every time. But in terms of numerical weather prediction, again, satellites are absolutely critical. Aircraft information is important. Ground-based systems, radar, Raywin-Sans. We ingest as much information as possible into our models to get the best initial condition. Data assimilation is something that is critically important. And basically what data assimilation does is it takes information in terms of observations, tries to create an optimal initial condition, so when you start a model moving forward integrating, you'll achieve your target, or in other words, your verification. And the best example I could think of to convey what data assimilation is, imagine yourself starting across the far side of a room. You have a target on the far side, an X on the wall, and you want to hit that target. Well, initially you see it, so you have the assimilation point, that's your analysis. Close your eyes and start walking towards that target. You're going to start to find yourself, you start to deviate from the solution. Open your eyes, you got a data point. So now you make an adjustment, you start heading towards that X again. Close your eyes, start working towards it, you're going to deviate again. So what data assimilation is, it just tries to get the model on course to the proper trajectory to reach the desired solution. And right now, what we run here is called at NCEP, is a hybrid combination between Ensemble, which gives you probabilistic information about the flow field, and variational, which tries to minimize errors between the observations and the background, which is a model forecast. And within a year from now, we'll be going to a 4D ENVAR, which other operational centers around the world have as well. Data assimilation is absolutely critical to a successful and skillful numerical weather prediction system. Physical processes. I want to talk about these because this is something that is very much overlooked. People get really focused on the observing system and data assimilation. Bottom line is that you have to have physical processes represented in your models. After all, models are nothing more than a mathematical formulation of the laws of nature, if you will. F equals ma, for example. And we have to worry about physical processes. The sun, radiation comes in, hits the ground, is reflected by the ground, some is absorbed by the ground, some goes into latent heat flux, evaporation, heating up the soil. We have clouds that we have to worry about. And when you get into clouds, microphysics, that's a very important part of getting the cloud field right. You have to worry about sea spray, interaction from the ocean, fluxes, heat and moisture. Convection is really important. We know that. And as models are coming down at higher and higher resolution, we're finding that we have to represent more and more physical processes in those systems. And quite honestly, in the academic community, the people, or I say the number of people that are really digging down into physical processes, I think has been on a decline for the last 20 years. And I don't know why that is, but it's a hard business. And field campaigns are really important, flying aircraft, getting measurements at different altitudes to really help us understand what's going on in these physical processes, so then we can improve our algorithms to represent them in models, right? Before you can predict anything, you really have to understand it. That's a really important part. That's where the observations come in. Fundamental science to understand those processes, and then numerical representations to try to get them as accurate as possible. And when you create a model, you always have to make assumptions. You're not going to get everything perfect. So When you make assumptions, you lose some information, you lose some accuracy. So that's kind of the dance that we play in the physical processes. It's absolutely critical to getting a good numerical weather prediction model. And then I'll talk about resolution quickly. Everybody gets real excited about resolution. And the reason is that resolution is important for physical processes, basically. So here's an example. Here's convection over the state of, I think it's just Kansas. And this is a relatively coarse grid. And each box or each X represents a grid cell, if you will. And you can see that for that particular cloud feature, there are 4 grid cells that capture that phenomena, that feature. And if you go to a higher resolution, you can see that you're going to capture that feature with more grid cells. And so it's like having a wire mesh, and you put a tennis ball on it, and if the holes in the wire mesh, chicken wire, are very large, the ball is going to fall through. Your model doesn't even know that phenomena exists. Yet if you have a very coarse mesh, it's going to hold the ball in place, and it senses everywhere where it touches the tennis ball, it's represented. So the higher resolution you have, the more that model's able to know that that feature is absolutely, or is actually there. If it's too coarse, it doesn't know it's there, it can't possibly predict it. So that's why resolution is extremely important. And a lot of people focus on horizontal resolution. It's also vertical resolution that's important as well, because you've got very strong gradients in both moisture and temperature and wind that are important to numerical guidance systems. So higher vertical resolution is just as important perhaps as horizontal resolution. And this is really important for physical processes as well. What happens is when we get models to higher and higher resolution, we're starting to resolve physical processes that perhaps the models didn't have before. So we have to start to add complexity to the models in terms of physical processes as we get to higher and higher resolutions. And with the current GFS upgrade going in at 13 kilometers, it was at 27, going down to 13. Everybody was very excited about that increase in horizontal resolution. But what we didn't do is articulate expectations in terms of the fact that when you make a change like that in resolution, you also have to make changes in your physical parameterizations, your physical representations. And typically, the biggest bang for the buck comes a year after you do a major resolution change, where you've had time to modify your physics, radiation, boundary layer, clouds, convection, to adjust to that increased horizontal resolution. And that's going to occur a year from now, and I'll talk about that later. Now I just want to talk about how the global model has evolved over time in terms of its skill. Now, what I'm looking at here is a frequency distribution of the annual mean anomaly correlations at 500 millibars. And I know a lot of people are frustrated by 500 millibar anomaly correlations. We don't live at 500 millibars, we don't live up there. But it's important because it's a legacy metric, and it basically tells you how your global system is doing in capturing the wave structure of the atmosphere, troughs and ridges. So it's really important. And basically what we see here is that each line runs from 1996 to 2013, and the colors go from the blue, the cold, which is early in that time period, to the more warm colors, which is later in the 2010, 2013 time range. And what you find is that the frequency distribution is increasing with time towards the higher anomaly correlations, which is a good thing. So what you see if you look to the left of the 0.7 dashed line for the anomaly correlation, as you go from the cold to the warmer colors, that line drops, which means you have fewer and fewer forecasts below 0.7, which is not very skillful. On the other hand, when you look at the 0.9 dashed line, you see that as time goes on, as you move from the cooler to the warmer colors, our anomaly correlation is getting higher in terms of the frequency. This just tells us that we kind of know what we're doing in terms of improving the global model skill over time. Now, the reason I talked about data assimilation, observations, and resolution in physics is because all those things are important in improving the skill of any numerical weather prediction system. And what I've got here is the percentage of the global forecast system 5-day 500 millibar anomaly correlations greater than 0.9. So these are the number of good forecasts that you get every year, or the percentage. The higher is the better. Let's focus on the red bars. Those are the northern hemisphere. And if you follow on through time, if you go from 1998, you could see that we made a resolution increase from 70 to 55 kilometers, and we got a bump up in skill. In 2006, we increased the resolution. We made physics changes in the land surface scheme. We got a bump up in skill of the forecast system. In 2009, we just made a change in our quality control in our data assimilation system. Bad data is a bad thing for a numerical guidance system. You want to keep the bad data out, get the good data in. So just a small change in quality control made a big impact in our skill. And then in 2010, we made a resolution change from 38 to 27 kilometers, modified the boundary layer scheme, modified convection scheme, and we got a nice bump up in skill. And then in 2012, we made a data assimilation change. And the point here is that when we do an upgrade of the global forecast system, it's not typically one thing that we change. And in the research community, a lot of people spend time changing one thing, which is fine. That's fundamental research. That's really important. However, in operations, we have what we call packages. When we do an upgrade, it's usually a package of many things that are systematically tested over time together and then evaluated as an entire package. And the point here is that it's not just one thing. It's not just the observing system. It's just not data assimilation. It's not physics. And it's not resolution. It's a combination of all those things. And that's something that I really didn't understand when I worked at NASA for 20 years. I like to focus on one thing. I'd make that change. It would have the desired impact. I'd write a paper on it, and then be on to the next thing. Well, if you look really carefully, what you'll find is that if you make a change somewhere, say in a boundary layer scheme, maybe you'll get better 2-meter temperature and better 2-meter dew point predictions. But you might also find that you've degraded your precipitation forecast. In fact, that's what I found at a tender age. And it was humbling. It was frustrating. That's why in operations, we have to look at it as a holistic package. So the development process. This is a convoluted diagram, but it is convoluted because it's a process. And so the global forecast system change that's going to go in on Wednesday, that's basically a 2-year process to get that upgrade. And what you see on the upper left-hand chart is the amount of systematic testing that has to get done to get an upgrade put together. And typically, it does start out as individual pieces. Somebody's working on the boundary layer scheme, somebody's working on the convective scheme, somebody's working on the clouds, somebody's working on the radiation, someone else on the land surface. So early in a development cycle, all those pieces are kind of going on independently, testing those at lower resolution. And then what we do is we look at which ones look the most promising. Not everything gets into a package. That's just reality. And that's kind of where the research community gets a little bit frustrated because they don't understand that in the end, everything has to work together. So the promising pieces will continue to evolve and move forward in the testing. And then eventually, everything has to be tested together. And it takes years to test those different packages together to make sure that there's no harm in terms of the quality of the guidance that's being provided. And then once that's all done, then we have several processes within NCEP to make sure that we have scientific integrity, we have review boards, we have IT testing periods, and then eventually the NCEP director, based on assessments from the customers, mind you, decides whether or not we're going to go live. And for the GFS upgrade on Wednesday, the decision meeting was just last Friday. And we received input from all the national centers. We received input from the Weather Service field offices and a couple other organizations. And I will say that expectations were really high for this upgrade. And I will say, and I'm going to show some results later, that the results were relatively mixed. Some parameters looked a lot better, others not quite as high as they had hoped. But that's just the reality of a model upgrade. This is an example of a test plan. This is for the Hurricane Weather Research and Forecast System. And what's unique about the HWRF, again, this is our regional model that provides intensity guidance for the Hurricane Center. And what I like about this is that it has an annual upgrade cycle. In other words, we upgrade it every year. And Vijay Talapragada is the hurricane lead at Environmental Modeling Center. And he works very closely with the Hurricane Center, who is the primary customer and user of this tool, and develops a systematic test plan based on the previous year's performance of that model. In other words, where was it performing well? Where was it not performing well? And what are the aspects of that system that we should be focusing on trying to improve? And that's why working with a customer really helps the model developers, because model developers don't look at it like a forecaster does. A forecaster has a different perspective than the model developers. But having them communicate is really important and beneficial to identifying what parts of the modeling system we should prioritize for improvements for the following year. And the reason I show this is because Vijay has developed a very comprehensive way to gather requirements from the Hurricane Center and develop a systematic test plan that takes months to test. And then we basically make thousands of runs of the HWRF system. We try different combinations of improvements. And in the end, we have to make decisions. Some things get in, some things don't get in before it gets implemented, typically in May prior to the hurricane season. This is something that I did not understand when I worked in the research community, is the systematic testing that had to be done, and then the fact that, oh, by the way, you have to satisfy a customer, right? People are using this tool in their processes, right? Delivering information to their customers and how important that is. That's something that I've learned over the last 6 years. And this is just an example of the HWRF system, Hurricane Arthur this past year. And I will say, because of the systematic annual development cycle of the HWRF system, and also due to the Hurricane Forecast Improvement Project that was funded through the National Weather Service, we were able to work closely with the research laboratories in NOAA and the academic community to bring them in together to work on priority areas for model development of the HWRF system. And I would say, because of that program, we have taken the HWRF system to new heights. And I'll argue it's the best regional hurricane model in the world today. And it's widely, international Met centers from around the world are asking us to come brief them on this system, and they're trying to implement it in their operations as well. But again, it's that systematic attention to detail that has helped evolve this system over time. Ensemble prediction. Basically, what I've talked about so far are deterministic systems. Ensemble prediction basically takes, when you have a model, an initial condition has uncertainty in it, has errors in it, because of the observations themselves, because of the background field, and then you move that forward in time and you have model uncertainty. And what's nice about ensembles is that you tweak the initial condition, you're going to get a different answer if you integrate it forward in time. So we've been very aggressive with ensemble systems. I know that a lot of you in this room, in the community, rely on ensemble-based systems. In 1992, NMC at that time implemented the first operational global ensemble forecast system. It had 3 members, 210-kilometer resolution, 18 layers, out to 240 hours. And then in 2001, NCEP was there, and they implemented the short-range ensemble forecast system that was composed of 10 members, 48 kilometers, covering North America out to 63 hours. So this is where the genesis of the GEFS and the short-range ensemble forecast system have come. Now, what's nice about the ensemble forecast systems is that they give you a sense of the predictability of the flow regime at that point in time and the probability of a likely outcome. And this is easily seen in hurricane tracks. A lot of you have looked at this information in the past. The system on the left, this was an example of Hurricane Katia. The white represents the ensemble mean, and you see a large spread of hurricane tracks. So obviously what this means is you've got relatively low predictability or relatively low uncertainty as to where that track is actually going to go. On the other hand, on the right-hand side, we've got an example where the tracks are relatively tight, they're clustered. And for that particular situation, you would have higher confidence in terms of where that system is going to go. And so this is where ensembles are really important. And you can also use this for precipitation type, precipitation itself, and mid-latitude storm tracks as well. This is an example of what we call postage stamps. These are 21 members looking at sea level pressure for 21 ensemble members at day 5. And what you can see is that for the majority, if you just look at them quickly, they look fairly similar. At least the majority of these analyses look, or forecasts I should say, look very similar. However, the ones in red are clearly outliers. That doesn't mean they won't occur, but they're clearly outliers. And one of the challenges in creating an ensemble system is getting a reasonable spread. And for years, forecasters and customers have told us that the global ensemble forecast system is under-dispersive. In other words, it just doesn't seem to really have a broad enough envelope of catching some of the more extreme events. And this is something that we're working on with the next upgrade of the global ensemble forecast system in terms of the perturbations to try to get a more realistic and a better spread so that that ensemble forecast system has a higher probability of catching the extreme events. Okay, shifting gears, Hurricane Sandy. This is a satellite animation of October 21st to the 31st of 2012. And we all know that Hurricane Sandy was devastating, a huge impact on millions of people, a very large, complicated weather meteorological event. Looking back, it was really amazing the ability of our numerical guidance systems to capture not only the probability of this event happening 7 days out, but within 4 days, how well the numerical guidance systems, and that's all of them, really locked in on the track and intensity of Hurricane Sandy. Now, this event not only had a profound impact on the U.S. in terms of impacts, but also operational modeling. So again, this was over 2 years ago now. And I think what this event did was it raised the awareness of operational modeling like never before. And the reason that happened was because the European Center, ECMWF model, catched on to the left hook of Hurricane Sandy towards the coast, farther out in time than did the U.S. Global Forecast System. That is a fact. And because of that capturing, there was a lot of discussion about the quality of the U.S. numerical guidance system. That's fine. And nowadays, there's a lot of attention on modeling, and it raised a lot of questions as to what are some of the differences between those two systems. Why did the European Center system catch on to that hook earlier than did the U.S. system? And I'm going to talk about that. But, you know, we're a public service. And there are a lot of people that blog about our products and services. And I must say that overall, the support is extremely positive. And I really want to thank the people in this room, and I want to thank the community for being advocates for what we do. Because I think everything that I've seen and everybody I've talked to, sometimes it comes across a little bit tough. But it's really to try to make us as good as we can possibly be. Because the better we are, the better you are. So we don't take it personally. I'd rather be talked about than not be talked about at all. And I would argue that since Hurricane Sandy, there's been a lot of attention on what we do, and I think it's been for the good. And sometimes, yeah, sometimes it's tough. But modelers are passionate. We're doing it in operations because we like having the work that we do impact the public on a daily basis. They're dedicated individuals. So looking at the European Center versus the Global Forecast System. Again, this is a legacy metric, the 5-day, 500 millibar anomaly correlation, 1984 through 2013. The lines of interest, and I apologize, it's a little bit busy. The Global Forecast System, this is the Northern Hemisphere. That's the red line. And you can see that all the models go up in time. That's consistent with what I showed you earlier. The European Center is the purple with the triangles. And what you see on the lower right-hand part of the diagram is a bar that represents 0.05 anomaly correlation points. And if I superimpose that on the diagram, what you see is that some years the gap between the European Center and the US system are larger, some years they're smaller, but overall the trend, when you go from the lower left-hand corner to the upper right, is that we are closing the gap. There's no doubt about that. And you can see that the ECMWF is kind of asymptoting. That's perhaps not too surprising. But yes, you know, these are some improvements that we made over time, and a lot of people get caught up on the deterministic metrics. These are two modeling systems. We're not even talking about the ensemble systems. So as we go forward in time, you have to keep in mind that when you look at two deterministic systems, and again, we're forecasters were kind of trained that way. I know when I was growing up and went through grad school, we only had one forecast. You know, we had a DIFAX chart, and that's all we could look at. We didn't have ensemble systems. And we're highly competitive, and we would just focus on deterministic systems, the model of the day, if you will. The point is that we're making some ground on the European Center. I believe we're moving in the right direction. And I believe, in part, because of the attention that Hurricane Sandy brought to the current state of the U.S. forecast system, that we're getting some additional resources to put towards improving that system, which, again, is foundational for the entire U.S. weather enterprise. So last week, we had an announcement at AMS. Dr. Sullivan, the NOAA administrator, talked about an upgrade that we're going to have for the operational supercomputer. That's NOAA's operational supercomputer. We have two identical clusters. One is the primary, the other is the backup. The backup is used for development of upcoming model upgrades, and it's also available so that if something happens to the production machine, within 15 minutes we can switch over to the backup without losing any products. And the reason that came about was because of a fire we had in 1999. Supercomputer went down. We were no longer distributing numerical guidance systems to anybody. And we learned our lesson there, and because the community advocated and said, look, we can't have that happen again. So in the early 2000s, we got an identical primary and backup system. Our current capacity is 0.27 petaflops. And a petaflop is 1 times 10 to the 12th, or 1 with 12 zeros. It's huge. These are floating points per second. Big numbers. In February of 2015, which is just the end of January basically, we're going to have an increase of about 3x. And this was a normal scheduled upgrade for the supercomputer. So it will be at 0.776 petaflops. And then the big jump comes later this year, in part because of increase in our budget and also because of resources put towards this asset by the Hurricane Sandy Supplemental, or the Hurricane Disaster Relief Act, is that we'll increase it to 2.5 petaflops. And this is per cluster. This is not aggregated. And that jump to 2.5 is something we've never seen before in NOAA. That's a huge increase in compute resources. And just going from 3x, that's about a standard. We get about a 3x increase every 2.5 years. So this is a big deal. And what the European Center has on the floor today, they have, again, a primary and a backup, just like we do in the US. Their current capacity is 3.6 petaflops per cluster. And that's what they have. So we're making a nice jump. Does it catch them? No. But what it does, it gives us an awful lot of opportunity to make some serious improvements in the guidance systems that support you. So again, this is something you've seen before. This is a production suite, 24-hour cycle. And what I want to do is just show you conceptually what kind of increase we're going to have in computing. And basically, when we add the GFS upgrade to this, we're going to be pretty much near the top of capacity. We really can't put much more on this particular machine. So at the end of February, or I should say the end of January, we're going to have a lot of increase. That's a 3x increase. A lot of room for growth, which is typical. And we'll consume that growth by increasing resolution of the GEFS, the short-range ensemble forecast system, and some of the other regional systems as well. And then looking forward a year, well, before I do that, an important point is that all that, what we call the white space above the production suite, that doesn't go to waste, that doesn't sit there unutilized. We use that to transition, run pre-implementation parallels, and transition that into operations, so that what happens over time is that you'll have systems running on the top of this diagram that will eventually, when they get implemented operationally, they go to the bottom. And so the bottom slowly increases with time. That's a natural progression and utilization of the machine. So we use that white space for transition parallels. And it's absolutely critical, because if we don't have that white space, we can't do our pre-implementation testing. This is what it looks like at the end of this calendar year, when we have a 10x increase. A lot of opportunity. And we are looking at this very carefully and strategically in determining where we're going to use this asset for the major components of the production suite. A lot of opportunity. Major model upgrades for 2015. We, again, have marine systems, atmospheric systems, land systems, dispersion. And I want you to focus on the bottom part of the diagram. These are the major pieces that we're going to do this year. The global forecast system and its ensemble system, increasing the resolution, we're improving the data assimilation system, physics, and we're making a change in the dynamics. The RAP, the rapid update, and the high resolution rapid refresh. We'll be making some changes in the data assimilation system and the physics there. That's a continual improvement. The short-range ensemble forecast system, we're going to be adding some members to it. It's currently 21. We're going to add 6 members to it. But keep the resolution the same, because we did a trade-off and decided that we'll get more out of the system in terms of the spread of the ensemble by adding more members. And then the North American model, we're going to go to a 3-kilometer CONUS nest that will position us to develop the 3-kilometer high-resolution rapid refresh ensemble in the next 3 to 5 years. Just kind of getting close to the end now, the global data assimilation system, the upgrade that's occurring Wednesday. Jim Cantor and I were talking last night, and he says, well, what's this all about? Is this really going to be a lot better than what we have today? And that's a fair question. And I think one of the things that I'm learning sitting in the NCEP director position is that we need to do a better job communicating the changes that we're making to our systems, giving the user community early access to that information, giving the user community early access to the data sets so that you can look at those in your decision support system, so you have a better understanding of what changes are coming, so that you're not surprised when you get them. We've done that with the service centers, we've done it with the regions, but we've got to do a better job reaching out with the weather enterprise as a whole. So this upgrade, again, it's a package. We've gone to a similar Lagrangian formulation, and basically what that does, it allows us to go to higher resolution with lower compute resources. This is something that I think most of the other operational modeling centers have moved towards many years ago. We're finally getting to it this year. So we're going to be running high resolution at 13 kilometers out to day 10, and then we degrade the resolution because there's less skill out there, and then we'll degrade to 33 kilometers. So we're going higher resolution. We used to degrade the resolution at day 8, but we're now keeping it high to 10 and then degrading it past that. And again, we got some radiation changes as well. Data assimilation and the analysis, we're improving the spread of the ensemble component of the analysis. That's an important part to getting a better initial condition. And we're increasing the resolution of the ensemble members as well for the data assimilation system. And we're also changing and improving the way we use observations. GPSRO, improved quality control. We'll be simulating some more satellite data than we were before. So you can see that it's a very complex interaction between parts of the system, and it truly is a package. Some test results. Again, this is a legacy metric, and when you look at the two top diagrams, again, this is Northern Hemisphere and Southern Hemisphere, 500 millibar anomaly correlation. We ran 659 parallels for this. That's over 2 years worth of retrospective runs of this package. I think that's unprecedented at NCEP. We ran 4 hurricane seasons to make sure that there's no degradation in the hurricane tracks for the Hurricane Center. And what you see on the bottom half of these diagrams is a difference with respect to what we're currently running operationally. The red boxes represent statistical significance. So when that red line on the bottom is outside of those boxes, and when that red line is above the solid blue line, that represents statistical significance improvement in this metric, which means that we're doing a better job with the higher resolution in terms of the wave structure in the atmosphere. So that should be a better progression of waves, a better representation of amplitudes. So this gives us confidence that we're on the right track and that the large scale is doing a good job. And we've got a even bigger improvement in the Southern Hemisphere because we made a change to our data assimilation system there. So I think we're going to see radical improvements in the Southern Hemisphere. As I said, all the national centers do an assessment. They take the information, they look at parameters that are important for their mission. What's important to the Climate Prediction Center may not be important to the Weather Prediction Center or the Hurricane Center. So everybody has a different perspective, and I just want to share some of that with you. For the Climate Prediction Center, their interest is really days 1 through 15. So they're looking at the longer lead times. And again, we're looking at anomaly correlation. I apologize for the quality of this image, but I just wanted to throw it in based on my conversation with Jim last night, is that the Climate Prediction Center looks at this, and they use this to decide whether or not they support this implementation. So the red line is the new system, so if the red line is above the black line, that's an improvement. And what you can see for the most part is that in the out time, beyond day 7, Climate Prediction Center was satisfied with the fact that this upgrade is better than what they currently use operationally. The Weather Prediction Center, extratropical cyclone tracks are really important to their mission. And so what we have here is the track error for extratropical cyclones. And this is for a period June through November of 2014. Lower is better. The blue is the parallel, these track errors. The red is the operational, so blue lower than red is good. Again, this is a metric that's important to them, and I said he's nodding his head. It's in the right direction. It's in the right direction, so they were satisfied. The Weather Prediction Center was satisfied with this metric, as was the Ocean Prediction Center. Another important parameter is precipitation to the Weather Prediction Center. And what we have here are days 1, 2, and 3 quantitative precipitation forecast threat score, which basically tells you whether or not the precip is observed where it's supposed to be and has the right magnitude. And what you see on the left hand is November 9th through the 30th of 2014. Again, the parallel is in red, the operational is in blue. And in this case, we had mixed results. So the parallel was not always better than the operational. And that's just a fact of life. It's not always the case that you get an improvement in every single parameter when you make a model upgrade. That's a fact of life. We strive for it, we try for it, but we don't always get it. However, the Modeling Center does a verification of precip throughout the entire pre-implementation test cycle. And those results showed a positive impact in all the precipitation metrics. This was a small window, but it does give us, we have to acknowledge that we do have some areas that we have to continue to work on with this system. And I will say that some of the early testing for the next upgrade in terms of the physics, I think is going to deliver quite a significant improvement in the precip forecast. Again, That's the year plus one after we do a resolution change. Not everything's perfect. Hurricane Center is really looking at the hurricane tracks. And this is the Atlantic hurricane track errors for 12, 13, and 14. Again, the red line is the parallel. The green line is the operational. And we have slight improvement for the shorter lead times. However, you can see at day 5, there's a slight degradation. This concerns the Hurricane Center, especially as we try to extend the prediction of the hurricane tracks to days 6 and 7. And they acknowledged that. They weren't pleased about it. However, we have to consider everything in a holistic way, and we did decide to go forward with this implementation. And if we add in 2011, the errors are not quite as large in days 5, 6, and 7. We acknowledge that. And the Hurricane Center will also acknowledge that they use ensembles as well. This isn't the only tool that they rely on. There's a lot of other information. But they decided, based on the fact that, given all the other metrics and the fact that all the other customers sitting at the table said, okay, let's go with this. We're willing to take slight degradations in some areas for the improvements of today and the potential for improvement in the next year. We're going to go forward with this system. This is just an example of what the Aviation Weather Center looks like. You know, jet streams, that's really important to them. And they saw that the jet streams in the parallel were better defined, had better magnitude. Tropopause height's important to them. Convection, they thought it was a little bit better in the parallel than what we were getting operational. So they decided to go ahead forward. They liked what they saw. They encouraged us to implement this. But again, the point here is that every center looks at a different parameter. And we have to look at everything holistically. And with this upgrade, setting expectations, everybody got really excited about the resolution. 13 kilometers, wow, that's really good. It is good. But again, the devil's in the details, and we have to work on the physics and the data assimilation for the next upgrade a year from now. And another thing that you don't see here is that we spent a lot of time in infrastructure. Data passing, the I/O. We had everything in Grid 1, which is very large data sets. We compressed those to Grid 2. That took a lot of time and effort as well. So just quickly, the Ensemble, Global Ensemble Forecast System. Again, we're going to have a major upgrade later on this spring. Increased resolution, both horizontal and vertical. However, because of the demand of the user community to have a reforecast data set with the Ensemble Forecast System, we're going to continue to run the old one for at least 1 year, for one cycle, to provide customers with access to it until we develop a reforecast data set for the new one. We're in the process of doing that. Again, this is a new requirement that we respect and we had to make an adjustment for. Looking forward, there's a lot of questions. These are commonly asked questions. As our global systems get higher and higher resolution.
Before you move on, quick, did I see that right with the upgrade for the GFS? Is that every 3 hours instead of every 6?
That's the GEFS.
GEFS, okay.
Yes. Yes, we're increasing the grid resolution, the grids that we provide to be higher resolution and more frequent. That's correct. So things that we're doing, the global models are getting higher and higher resolution. And eventually what's going to happen is I believe that the global forecast system will start to take over the North American model requirements. And so we'll have two basic regimes. We're going to have the convective permitting, which is a high-resolution rapid refresh ensemble, right? 3 kilometers and less, rapidly updating. And then perhaps we'll launch a 3-day forecast, maybe a coarse resolution, to give people that information at the longer lead times. The Global Ensemble Forecast System, I believe, will eventually take over the requirements of the Short-Range Ensemble Forecast System. That's, I think, coming along. And then the Global Ensemble Forecast System will also start to extend out to 30 days. And I believe we're going to be moving to a coupled atmosphere, ocean, land system, and eventually ice to deal with the Global Ensemble Forecast System. The HWRF, the High Resolution Rapid Refresh Ensemble, that's coming. There's a high demand for that. severe weather forecasting, aviation community, and then emerging requirements in a week 3 and 4 time scale. And again, this is where the coupled atmosphere-ocean ice systems come in, extending the GEFS out to 30 days. The climate forecast system, we continue to develop that, higher resolution, more detailed coupling. And we also leverage on other Ensemble systems provided by other international modeling centers and really the academic community. And we partner with them in creating multi-model ensembles. The North American Ensemble Forecast System, or NAEFS, is one of those. And then the national, or the North American Multi-Model Ensemble here in the US. And we have other requirements that are coming in terms of hydrology, space weather, ecological modeling in the Arctic. These are emerging areas. The last slide. We're listening to what people say. We know that people are passionate about the models and that you rely on those on a daily basis. And we have to change our processes basically to be more communicative in terms of what it is we're doing, why we're doing it. These are tools that you use. Forecasters, I got an earful when I go out to the field and talk to them. They're passionate about what we do, but they just say, hey, you know, we observe things, we provide you with input. What do you do with that information? What changes are being made? What's the rationale? What characteristics of the tool will change, and how will that affect the decisions that they make? Stakeholders need time to adjust to changes in the quality of the tool. We got to do a better job getting information out sooner. And the 30-day parallel that we run right now at the end of an upgrade or pre-implementation cycle is really not enough. It's kind of an IT test to make sure that it runs without incident on a supercomputer 24/7. So we're listening to what people are saying, and I think you're going to see some changes over the next year to try to make this process more efficient. So we get a lot of advice. We have external advisory committees. I talk to academic community all the time. On one hand, they're saying you need to drop the number of models that you run. Then when I have a stakeholders meeting, they say, well, we need more products and services. We want you to be faster, and yet it's becoming more complex. I do believe that over time, we'll be able to simplify the production suite without sacrificing requirements. We've simplified in the last 5 years. Some of the models that we used to run, we don't run anymore. The ADA, the regional spectral model, we're in a short-range ensemble forecast system, they're gone. We have been simplifying things. We have to. And I do believe that in the next 5 to 10 years, NOAA will be moving towards more of a unified modeling system. That's the global piece, and then eventually perhaps you may still have to have a regional piece with nesting for the convective permitting. But again, we're trying to simplify so that we all try to work on common systems. And I think that's going to make us better. So with that being said, I appreciate your interest. I appreciate the opportunity to speak with you today. I'll be here for a couple days and be able to address any questions that you might have. So thank you.
Bill, this is great. Thank you very much. Now you can take a drink of water. By the way, the hotel here is at 9,600 feet, so everybody please drink lots and lots of water. I'd like to open up the floor now for questions, and I just encourage you, please raise your hand so we can get microphones to you so the online viewers can hear your questions as well. And just please identify yourself before you ask the question. Thanks. Howard.
Bill Howard, Bernstein, Washington. Just for history, and it's great that we're catching up to the European, but why was the GFS so far behind the European modeling as far as computational power? What happened? And I see we're getting out of it, but I'm just curious why we were there in the first place.
It's integrated over time. The amount of resources we had available to develop that system were really not comparable to what the European Center has. They have, their focus is to be the best in the world at medium-range weather prediction. That's their goal. It's stated on their webpage. And so they don't have the regional systems that we have. So not only did they have more resources, more over time, it's dedicated to basically that one part of their mission. So I think there's more attention on the global system today than there's been in the past, which means we're putting more people on it, dedicating more computational resources towards it. So that's one thing. And also our data assimilation system, We didn't go to a more advanced data assimilation. We should have done it sooner, but we've done a little bit later.
One follow-up. Well, you obviously are part of the American government. Seems like the world relies on these models, not just the U.S.
That's correct. It's amazing how many people use our data, which is freely available to anybody who wants it, to initialize local models around the world for Met services. So in 2012, when we made an upgrade to the GFS, there was a problem in some of the output files. And we started to get emails and phone calls from around the world saying, hey, we can't initialize our models anymore. So we understand the global impact of what we do. Yes?
Brad Panovich, Charlotte, North Carolina. 2 questions. First one about the GFS. Thank you for making the parallel available publicly. It's been great following it for quite some time. But this argument about running it only twice a day over 4 times a day, like the Europeans, what are your thoughts on that? Do you think there's any value to that?
So my understanding, this predates me, my understanding for the rationale to run it 4 times per day was to meet the requirements of the media. That's my understanding. There was a demand for it. You know, you have different media across the coasts, and so they wanted access to timely information. So I think NCEP responded to that request.
The other question, you made a good point about the data collection and observations. What are your fears about the satellite data and our lack of funding for that, and how it could impact the modeling going into the future?
So NWP is just one part of the problem. And one of the ways you mitigate potential loss of information from satellites is to have a robust data assimilation and modeling system, right? To take full advantage of the information that you have available to you. So that's one of the mitigation strategies that we're doing, and it really was an outcome of Hurricane Sandy. We're putting more people on data assimilation, model physics for the global forecast system than ever before. So that's one of the mitigating strategies. It's a good question.
Bill, Joe Murgo from WTAJ-TV in Pennsylvania. The announcement of the GFS and the amount of petaflops increasing is big, but is it true? Is this just a catch-up? I guess I just, through social media and talking about it, found out that the European is going to announce going well beyond the 3.6, and the UK Met is actually going to 16 petaflop. And so, are we taking 2 small steps while other people are taking bigger steps? And to follow up, and I'll let you answer it all. Is there a difference between us, kind of just, they're almost a private enterprise for their model. Do they have a better model in their model system?
So I'm fortunate, on behalf of the government, we're fortunate to have the resources we have. And we put a lot of money into modeling in the last couple of years like never before, and it's up to us to make good on it. So that's one piece, and I believe we will. I like what I'm seeing. I like the fact that we have resources to engage the academic community in a way like never before. That's good. Computing, again, what we're seeing, this 2.5 petaflops is unprecedented here in the US. Let's make good on that. Let's show what we can do with that before we start complaining or anything like that. So I'm pleased to have access to that asset. What the other countries do, I can't control that. That's, they're always going to be increasing their resources, no doubt about that. But the European Center, their model, they spend a lot of time on data assimilation, quality control. They assess that model on a daily basis, and when they're in development phase, they have a dedicated group of people that are assessing it 24/7. This is something that we've not done well enough at NCEP. This is something where I'm putting people on it. And we've kind of, with this GFS upgrade, we've had more eyes on that, I think, than any other global upgrade we've had before. The field, the Weather Service was aggressively looking at it. People were putting it on their websites all over the country. So that's a good thing. And the last thing I say about the European Center, again, they have more people working on the global system than we do in this country. That's because it's their mission. They don't have to worry about the regional systems. That's their business model. And also, they're very good in terms of rewarding the scientists that come to work on that. They're paid extremely well. They get the best across Europe to go work there. And then they also invite the academic community to come and work on priorities that are set by the operational centers. So it's extreme alignment in Europe in terms of working on that modeling system. Here in the US, there are a number of different modeling systems. Academia and researchers are looking at different pieces of it, and there may not be a lot of motivation or desire, in some cases, to work on an operational system. It's hard. It's not easy. But I think we're getting better in this country. I think we're getting better aligned, and I'm really optimistic about the opportunities we have, and we have to deliver on those opportunities. And I want to thank everybody in this room and outside that have been advocates for this. You've stood up. You said we have to do better than we're currently doing. And I think that's why you see that 2.5 petaflop machine. So we have to take advantage of that.
Jim White, University of Colorado, made an interesting statement that as the resolution in time and space gets better and better in these models, that our understanding of the physics that happens at those levels needs improvement. Could you elaborate on that? Because I think that gets back to the answer you just gave about how the scientific community in Europe is integrated into the forecasting community there. Can you elaborate on what you see as the challenges and why we're not meeting those challenges?
So that's a great question. So the high resolution rapid refresh is a 3-kilometer grid spacing that's run over the CONUS, initialized every hour. And so what you're getting now is you're getting these guidance systems that are getting at the resolution where they could start to predict the mesoscale banding and those kinds of features, something that's very important in detail. But what that means is that you have to get the boundary layer right, because a lot of it's tied into the boundary layer, processes in that. So any deficiencies in your boundary layer numerics is going to give you inaccuracies in getting those mesoscale features right. So that, as you get to those higher resolutions, you're starting to resolve features that you have to get in the models. And that's part of it coming down. I hope I answered your question. Does that make sense?
Do you see this as a challenge for the future? I mean, are we investing enough in the basic research that we need to improve these models as the computers get better and better and faster and faster?
That's a great question. As the director of NCEP, I will say that I am concerned about the model developers of the future. When I was a grad student, I was thrown into the mix. You run the code, you got thousands of lines, and you have to figure out what's going on, right into it. And that's at a time when the models were simpler. You didn't have a lot of physics options, flipping switches and everything like that. Then you really had pure model development. And then what's happened in the last 20 years, really, we got community models, and those are great. People can download the weather research and forecast model. I could run it on this laptop. My daughter could do it, but that doesn't make her a modeler, right? You have to have an understanding of what a model does, what the physical processes are, in order to make changes to them. So I am concerned that we're not spending, at least the academic institutions, there are some that still do it, but we're starting to lose sight of real, true model development. We have model users. I think we're educated a generation of model users, which they download it, they flip switches, different physics options, and off they go, and they run a case study, tweak or tune one different thing, and then they publish a paper. But true model development, I'm a little bit worried. I'm a little bit worried. But I will tell you that I am working closely with the academic community to try to help identify those programs that perhaps with a little bit of tweaking could get back more into the model development. So there's hope.
Hi, it's John Morales from WTVJ, NBC6 in Miami. After Sandy, of course, there was a lot of attention put on our modeling capabilities and GFS versus European. And there was also quite a bit of attention placed on the ratio of short and medium range modeling versus long range climate modeling at NCEP. How did NCEP respond to that, and what's the current state of that ratio?
So I think the operational computer is the weather and climate supercomputing system. So there is a climate component. But NCEP's climate component really stops at the less than 1 year. That's what our mission is. It doesn't go beyond 1 year. And we haven't changed the amount of computing that we put towards climate since 2011. We are developing the next version of the climate forecast system, which will be higher resolution. There's no doubt about it. It'll be computationally more expensive. But I do believe that we could apply that on a lower cost, high performance computing asset than the operational supercomputer. I don't think you need to have as timely, as timely information. You could run it less frequently, perhaps. The higher resolution stuff that we're running, the high impact events, the hurricane, the convective permitting, you need that to run on time every time and the data getting out as quickly as possible just because of the time scale of the phenomena. So, I think we've done what we've been asked to do. I think it's strategic, and the climate forecast system will continue to evolve because there's a demand for products and services in that week 3 and 4 and beyond time scale. That's not going to go away.
Thanks, Bill. Dave Titley, Penn State. Just sort of maybe taking a step back here on some of these questions about models and our models versus Europeans or other numerical prediction centers. For NOAA, for the Weather Service, is your philosophy to aim for requirements that are defined in an absolute sense, as in we need to forecast hurricanes, let's say less than 200 kilometers at day 5 area and within X knots intensity, or is it a relative requirement in that whether we're good or bad, we're going to be the best in the world or the second best in the world? So are we aiming for absolute requirements or relatively requirements, and how is the philosophy within the Weather Service and NOAA on that?
That's a very good question, and I think what I've learned in going through the strategic planning process is that our gathering and definition of requirements needs to get better. That's a tough process. And what I've seen within the National Weather Service, for example, again, we're geographically spread out. NOAA has the research component, which sometimes inadvertently sets requirements for the Weather Service. That can happen through hallway conversations, quite honestly. So one of the things that I want to do at NCEP is and I believe Dr. Uccellini agrees with this, is that we have to get better in gathering requirements and vetting those requirements to make sure we're prioritizing the use of our assets. So we need to get better in the way we develop and gather requirements. It's not been as systematic as it needs to be, in my opinion. But again, I'm optimistic about the direction.
Jennifer Zeppelin, Chief Meteorologist from Tulsa, Channel 8. And one of our storm chasers was actually wondering, he was just asking, I wonder how much the data that NWS actually relies on the European system for forecasting up to like 196 hours out. Do you guys rely on that? Obviously you look at it, but how is that in comparison with the other models?
So the European Center guidance is good. And it's available to the Weather Service forecasters, and it's used in their decision-making process, just like the UK Met model, just like the GFS and all our ensemble systems. So again, this goes to the fact that sometimes we get too caught up in a single deterministic, right? When I was a forecaster, I would get as much information as possible because it's a very competitive thing. You want to put the best forecast together, and as a forecaster, you're going to use every piece of information available to you. So the European Center model is used by the National Weather Service. I know the ECMWF, Europeans use our model guidance in their processes as well, as does the UK Met Office. So it's part of the process.
Okay, Bill, this is Dave Jones. I know we're running a little bit over, but the discussion is excellent. I had one quick question for you, and that is, with all of these model upgrades, this exciting output coming, how are you positioning NCEP to deliver all of this data to the folks in the room here, whether they're broadcast meteorologists or to other users? How will they access that information? Are there upgrades needed on that end as well?
That is a big challenge. And that's a big question. We can torque up resolutions of systems, and if we can't get the data out to the end user community, it doesn't really mean a lot. So this is the big data challenge that we're facing in government in general. And so with the high resolution rapid refresh, for example, the AWIP system has limited bandwidth that you can get grids to the forecasters. So what we did was a year ago, we met with the regions, NCEP did, and decided on what parameters, what fields, what the weather forecast offices like access to. And we down selected those, we worked really hard with the regions, and the minute the HWRF went live, those data were available to the forecast offices through AWIPs. And that's kind of a crisis reaction, if you will. But going forward, we got to find ways that people perhaps can come in and query the data sets through analytics and take out the information they want from those data sets and bring it back for their professional use. We're not there yet. I believe we're fairly close. We want to work with private industry to address that issue in creative ways that's fair to everybody. Again, we have to give equal access to the information. So, pushing these large data sets around is certainly not viable, but allowing people to come in, query the data sets and pull out what they want and just bring back that piece of information, I believe is the way that we need to move forward. So big data is going to be a big challenge for us, no doubt about it.
Bill, thank you very much. This has been terrific. And what we're going to do is we're going to take a break, just about a maybe 5-10 minute break, then we'll be back. And I just want to also let the online viewers know that we'll be bringing both Bill and Dave Titley back for about a 20 to 30 minute session where you can ask questions directly from the internet just a few minutes after Dave Titley finishes his talk. So we're going to take a little bit of a break. Online viewers, stay with us. We want you to experience BREC a little bit, so we'd like you to take a look at this video, and then we'll bring up the schedule afterward. We'll be right back after this.